The stellar occultation curve broke mid-observation, and every prediction line on the screen became unusable at the same moment. Multiple Earth-based observatories confirmed the same failure. At Lowell Observatory and partner stations across the southern hemisphere, telescopes tracking Pluto's pass in front of a distant star watched a clean, forecasted dip turn into something no model was designed to handle. The light curve should have descended smoothly, a gradual signature of a thin, extended atmosphere bending starlight. Instead, the signal hit a sharp break, a sudden step, as if a physical layer around Pluto had stopped behaving like a continuous gas and started behaving like a boundary. NASA-affiliated analysis teams flagged it immediately. Not as noise, as contradiction. The visual on every monitor was identical. A clean, stellar light curve suddenly flattening into an abrupt step change instead of a smooth decline. That single line on the screen became the problem no one could ignore, because the instruments were not disagreeing. The universe was not ambiguous. The interpretation was collapsing in real time. The pressure was immediate. If Pluto's atmosphere behaved like this, then every previous occultation interpretation in the outer solar system carried an unspoken error, and no one had accounted for that scale of systematic failure. The first reaction was procedural. Recheck timing. Recalibrate atmospheric scale height assumptions. But the curve did not move. It stayed broken. And that is where the real problem began. The data did not just show a change. It showed a change happening inside a system everyone believed was slow, stable, and predictable. A clean stellar light curve suddenly flattening into an abrupt step change instead of a smooth decline. The line stayed frozen on every screen. And now it meant something different. Because Pluto was not behaving like a distant frozen world with a thinning haze responding gently to sunlight. It was behaving like a system crossing a threshold, a boundary being reached inside the measurement window itself. The observation was no longer about Pluto alone. It was about the assumption behind every outer solar system atmosphere model used for decades. At the University of Hawaii Observatory feed, a senior analyst compared real-time curves against archived occultations. The earlier datasets looked consistent only because they had been forced into smooth models. The new curve refused that correction. It resisted smoothing. It resisted averaging. It stayed sharply discontinuous, like a step had been carved into the atmosphere itself. And then the visual anchor returned again. A clean stellar light curve suddenly flattening into an abrupt step change instead of a smooth decline. This time, it did not look like an anomaly. It looked like a boundary condition. The interpretation began to shift, slowly at first, then all at once. If the atmosphere was collapsing or condensing rapidly along Pluto's limb, then the old assumption of gradual scale height was not just inaccurate, it was structurally wrong. Every earlier smooth curve might have been a limitation of sampling, not reality. But the system still resisted that conclusion. Because a rapid atmospheric transition at that distance implied a physical responsiveness no one expected in such cold, weak sunlight conditions. So teams tried to stabilize the model instead of replacing it. They introduced layered corrections, thermal lag adjustments, seasonal sublimation rates, even alternative haze scattering profiles. For a brief window, the curve appeared to fit again. That moment felt like control returning. Then another occultation pass arrived. Same star, same geometry, different result. The curve did not soften. It snapped again into the same abrupt step. A clean stellar light curve suddenly flattening into an abrupt step change instead of a smooth decline. Now the repetition removed comfort. It was not a one-time event. It was a behavior. And that forced a larger realization. The system was not witnessing a single atmospheric collapse. It was witnessing a repeatable transition state in Pluto's upper layers, triggered by orbital position and solar exposure. Something inside the atmosphere was not responding gradually at all. It was switching. That shift expanded the problem beyond Pluto. Because if one outer solar system body could cross from extended atmosphere to condensed collapse within a single observational window, then every distant occultation dataset carried an embedded uncertainty no one had quantified. Mid-analysis, the scope widened. Voyager-era assumptions were pulled into review. Ground-based survey archives were reprocessed. The same pattern appeared in old data, but it had been smoothed out by earlier processing pipelines that assumed continuity by default. And again the screen showed it. A clean stellar light curve suddenly flattening into an abrupt step change instead of a smooth decline. Only now, it was no longer just Pluto in question. It was the measurement philosophy itself. As new modeling attempts escalated, the atmosphere signature refused to stabilize into any single curve family. Instead, it behaved like two states occupying the same observation window. One extended and refractive. One collapsed and sharp-edged. The transition between them was too fast for classical thermal models to resolve. Observatories began to treat the curve not as a profile, but as a switch event, a boundary crossing, not a gradient. But that reframing came with pressure. Because once you accept switching behavior, you lose the ability to infer continuous properties from a single occultation pass. And then the final pass arrived. The geometry was perfect. The instruments were stable. The star disappeared behind Pluto with full expectation of a smooth atmospheric signature. Instead, the signal hit the same hard break again. A clean stellar light curve suddenly flattening into an abrupt step change instead of a smooth decline. And this time, there was no model left that could absorb it without breaking. The consequence was no longer about Pluto's atmosphere alone. It was about every assumption used to translate starlight into physical reality across the outer solar system. If the atmosphere could collapse or transition within a single observation window, then slow changing was never a law. It was a convenience imposed by sampling limits. The final realization settled across every control room watching the same frozen line. What looked like stability in past data was not stability at all. It was a missed transition hidden by resolution. The last recorded frame from the campaign held the same image, the same curve, the same impossible step. A clean stellar light curve suddenly flattening into an abrupt step change instead of a smooth decline. But now, it no longer described Pluto. It described the limits of what had been trusted as measurement. And the final thought in the data logs was simple, sharp, and unavoidable. The atmosphere did not fail slowly. It changed faster than we could see.